Okay, so this is Availability Workbench. To give you an overview of what this tool is, it's a suite of different software tools for different aspects of RCM and RAMS analysis. The program uses Monte Carlo simulation, and the advantage of that is it lets you perform RAMS analysis and what-if analyses. Basically, you can model your maintenance, model your system availability, and use this to select the best possible maintenance strategy, and also help you maybe improve things like system design and spare part storage and things like that. So the different modules of Availability Workbench are listed here in the module selector. The two modules I'll look at today, the ones that I think most suit your requirements, are RCMCost and AvSim. RCMCost is a tool that's focused on helping you select the best maintenance strategy, and it can do this based on cost or availability, and taking into account resources, the cost of failure, criticality, and so on. AvSim, or availability simulation, can take it a step further and allows you to construct a logic diagram that represents the relationships between the equipment and your system. So if you need to model complex dependencies, like say redundancy, shared spare parts, and things like that, you can model it in AvSim, and you can get sophisticated availability predictions that can help you to, again, improve your maintenance, but also improve the design of your system as well. So we'll take a look at that too. So RCMCost allows you to build a functional location hierarchy that represents your system. And you can see you have the tools to do that here. You can add locations that represent your sites and equipments. You can specify the functions and the functional failures of those equipments, and also you can create causes that represent the failure modes of those equipments as well. Now, that information can be constructed manually, but you can also import that kind of data from other sources. So, for example, if you say had a bill of materials that was stored in Excel, we have very powerful import and export facilities. So here, for example, you can see you could import your data from Excel or from Access. So those options are available to you. If you're using one of the big asset management systems like SAP or Maximo, there are also portals available for those as well. So you could also import your data from one of those systems, and that could actually be used to almost completely construct an RCMCost project with relatively little input from yourself. But I'll give you a look at what this information would look like once you've constructed it in RCMCost. So I will open an example project. So this is a fairly modest RCM hierarchy. You can see it's constructed from locations that represent the sites and the equipments, the functions, functional failures, and failure modes of those equipments. So if I open a location, for example, you can see here I can give it an ID that might represent, say, the part number, the description, so I can specify what type of equipment that is, and there are notes fields for additional information as well. All of these headers are customizable, so you can modify those to say something more appropriate to what you're doing if you wish. For the equipments, I can specify functions that just describe what that equipment does. This doesn't really affect the analysis as such. It's more information for your own benefit. The same is true for the functional failures. So if I open one of those, you can see a description of the functional failure. And each equipment can have multiple functions. Each function can have multiple functional failures associated with it. And then beneath the functional failures, you can have the failure causes or the failure modes of your equipment. Now, from a technical perspective, these hierarchies can be as big as you want. There's no upper limit placed on the number of locations or causes or on the number of levels of structure that you can have. So these location hierarchies can be as big as you want. Hypothetically, the only limit you might reach is the limit on the amount of memory that your operating system can allocate for the analysis. But if you're using a 64-bit operating system, there is a 64-bit version of the tool available. That's actually the one I'm using here. You might be able to see that at the top. So as I mentioned right at the start, Availability Workbench uses Monte Carlo simulation to simulate your maintenance and the availability of the system. So in RCMCost, what the program will do is it will simulate the failure modes and the associated maintenance in order to help you select the best maintenance strategy. So here, for example, I have a failure mode which I might want to look at. I can double click that to open it up. Now these causes are where most of the quantitative data goes into an RCMCost analysis. For example, if you look at the failure tab, this is where I can tell the program about the failure behavior associated with this cause. And there are different ways of approaching that. One, of course, is that you can enter that information manually. So you might know that a particular asset behaves a particular way. You can choose the relevant failure distribution and then enter the relevant failure parameters. Here, for example, I might be modeling a bathtub curve for this particular failure. So there are maybe also two extremes at which you might find yourself. At one end of the scale, you might be in a position where your system is brand new and you don't have any real information about how this system behaves. So you really don't know much about the failure behavior of this equipment yet. In that case, you may be in a position where you are using your own experience and the insight of maybe consultants and colleagues to try and anticipate how this equipment might behave and make essentially educated guesses to help you get started with your analysis. One of the ways the program can help you with that is through the failure distribution wizard, which is this button here. If I click on that, you can see I can choose to model one or more regions of the bathtub curve. So you will see these tabs kind of appear and disappear as I make selections here. So I can say, well, okay, I know from previous experience with other systems like this that this equipment usually follows a bathtub curve. So I can select the relevant regions, and then I can say, well, for the random failures, I've seen in the past that maybe these fail on average every 10,000 hours. So I might say the failure rate is about 10 to the minus 4 in that region. I might say, well, I expect these assets to start wearing out after about 5 years maybe. So 5 years of operation, it will start to wear out. And most of them might have worn out within 2 years of that time. So again, all of this is just coming from me discussing it with colleagues and with consultants. And finally, I might say, well, what's the infant mortality period? Well, maybe we have some difficulties in the first 6 months, perhaps associated with, installation problems, calibration problems, problems with new equipment in a particular manufacturing batch. And I might say the failure rate during that time is a bit higher, maybe 10 to the minus 3 instead. So once I've entered all that information, I can click OK, and you can see the program will populate the tri-variable distribution with the data that I've provided. Now on the other end of the scale, what we have is the viable data set. So this is what you might use if you have years worth of historical failure data available to you, maybe in an asset management system, or maybe stored in something like Excel or Access or SQL Server, where basically what you've done is every time you've installed an asset, you have made a note of that, of the date and time, and then when it failed, or when it was replaced as part of maintenance, you've logged when that took place. So what you can do is take that information and use it in the simulation to make it as realistic as possible. So if you were to purchase RCMCost or AvSim, you would automatically get the Viable module with that. What the Viable module lets you do is import historical failure and maintenance data, perform a line fit to that data, and then use the results as failure information for your simulation. So here, for example, I've got a failure data set. At the bottom, we can see the data that I've imported. Now, I can import the data in one of two formats. Here, I've imported the data as a list of times to failure. So every time an asset failed, I've logged how long it lasted for. Alternatively, I can import the installation and failure dates, and then the program can infer the time to failure from that. And again, if the equipment was removed or replaced as part of a maintenance plan, then I can just mark that as being a suspended data point. So that's right censored. So the program will still take account of the presence of that data point, but it may not have as much of an impact as, say, a failure data point would. So the program plots that data on a cumulative probability plot, and I can just choose the distribution I want to fit that data with, and you can see there the program generates the failure parameters from that data. Now, if you have a lot of data, you might be able to use the distribution, the automatic selection option. Here, the program will select the distribution which fits the data the best, but it's a good idea only to use this if you have a lot of information, because of course if you don't have many data points, then maybe that selection won't be so reliable. So you always have to use your own discretion when selecting a distribution, whether you're using the software to do that or choosing one yourself. But in this instance, the program is predicting from the previous failures that the average life of one of these assets is about 12,000 hours, and that it wears out pretty much linearly over time. So I can go back to RCMCost, and for one of my causes, I can go into the failure tab, and instead of entering the data manually or using the wizard, I can just select the relevant distribution, and that will just pull in the failure data associated with that particular set of data. And if you've got a lot of data sets in your project, there is an option here that lets you search through them, either in a project, the current project, or in a library. I'll talk more about libraries a little bit later on. Let's say we've entered our failure data. Now we might want to look at maintenance. So every time you create a cause in RCMCost, automatically the program will also create a corrective maintenance task. So that's the repair that takes place after the failure. So if I open that up, you can see I can specify the duration of the task, the cost. I can even specify what state the component or the asset is in after that takes place. So it doesn't have to be as good as new. It might be as good as old or some intermediate level. So I'm not replacing the equipment. Maybe I'm just patching it up and making it a bit better than it was before. Now I can also specify the resources that are required for this. This includes labor, which you can see from the toolbar here. I can create externally to the task and then just choose what I need from the list. I can also create one from here as well. So I could create the type of labor that I need, specify the costs and the delays associated with using this person in the maintenance, and then add the number that I need to the list of resources. Now it's worth noting at this point that as you can see, there's a lot of detail that can go into a project, in particular into the maintenance. But it's worthwhile noting that you don't have to specify all of this data straight away. The program can run an analysis with very simple data, maybe just failure and repair, or very simple maintenance tasks, so you don't have to have all the resources straight away. If you start with some simple data, you can still get some simple predictions back. And then when better data is available, you can just add that to your project and improve the results that you're getting back. So all of this stuff isn't mandatory, but it is optional, but it's useful to have this data because, of course, it will make your results more realistic. So as well as labor, you can specify equipment. Equipment is basically the tools you're using for the maintenance, and the input data is pretty much the same as for labor, so costs and delay times and things like that. And we can also specify any spare parts that we might need as well. So I can add a spare. Again, I can choose from the spares that are already in my project, or I can create a new one. And here you can see you can specify maybe the cost of buying a new spare part. And you can also talk about the number of spares that you can store and how much that will cost. This is handled on level 1 and 2. Level 1 is typically on-site storage, so these are spares that you're storing locally. And you can say how many you can store, how much it costs, how long it takes to get the spare from storage. Level 2 is similar. This is now what you might think of as off-site storage. So if you were dealing with, say, a rig at sea, level 1 might be the spares you keep on the rig. Level 2 might be the spares you have stored on land. Level 3 is typically the supplier. So here you would specify how long it takes to get resupplied by the person supplying the spare parts. You'll notice there are a lot of grayed out fields. These are only used by AvSim, so you might see those again later. But at RCMCost, you don't have to worry about these. So you can add the spares, choose the spare you want, say how many you need, and again, add that to the resources. And you can build up a list of resources that are required for each task that you create. So if during the simulation there is a failure, then the corrective task will be triggered to fix it. However, you may also want to model your preventative measures as well. So for example, you might have planned maintenance in order to prevent failures from occurring. So I've got a planned maintenance task here, which I can create just by clicking the New button. I can specify how frequently that task takes place using the interval. Again, I've got these costs and durations I can specify, and I can specify what resources I need as well. So I can say what I'm doing, when I'm doing it, how effective it is through the Advanced tab as before. So I can model my planned maintenance in that way, and I can add more planned tasks as well. I can have as many planned maintenance tasks as I want per cause, and I can use the Enable checkbox to turn them on and off and see which options work best. I can do the same for inspections. So inspections are similar to planned maintenance, but now there are no spare parts because we're only inspecting the equipment. And we have the Predictive Data tab for condition monitoring. Now the inspections can actually perform two functions. One, it can act as a means of finding hidden failures. So if on the Failure tab you've told the program that this failure is dormant, so you can't detect it straight away, then you might create an inspection to represent the task you perform to look for these hidden failures. In the event that the inspection finds a hidden failure, it triggers a corrective task to fix it. You can also use inspections for condition monitoring. So you can provide P to F data to tell the program how likely it is that this inspection will find a problem, and in the event that it does find a problem before failure, it will trigger any planned maintenance tasks with the secondary action checkbox turned on. So you can use that to model any tasks that take place in order to detect failure before it occurs. So you might be doing, say, vibration tests or checking for hotspots in an equipment and spot failures before they occur. And there are other types of strategy you can model as well. Conditional alarms, which function similarly to inspections, but instead of inspecting at regular intervals, now you're monitoring the system continuously. You can look at commissioning. So if you're dealing with a bathtub curve, you might have a commissioning run in order to remove infant mortality from the system. And you can include the cost of any redesign that you do. So if you modify the design of a system, you can include the cost of doing that as well. So we've talked there about the cost of repairs and the cost of doing maintenance, how we can apply that through the resources and things like that. But we haven't really talked about the cost of the failure itself. So say, for example, the cost of losing production or the cost of maybe being fined for not meeting with your safety requirements. This is handled through the effects, which you can see down here. So I can create effects very easily from the toolbar or the add menu. If I open one of these up, maybe the fire effect, so I can create an effect that represents a fire resulting from maybe one or more of the failures in my system. I can specify the costs associated with that. I can also specify the severities. So if this particular effect has a safety impact, as you would expect a fire would, we can specify quantitatively how severe that effect is. Now you could choose that as being a kind of dimensionless scale, where maybe 1 is a best case and 100 is the worst. Alternatively, often people might say these things represent something real. So for example, safety severity might be a number of fatalities that result from a particular problem. And we can enter that per occurrence or as a rate. We can actually use these together if you want as well. You can fill in any combination of these fields that are appropriate for you. So you can specify the cost and severity of that particular impact, that particular effect, and then you can attach these effects to your causes. So if I open my cause again and look at effects, you can see I've attached a couple of effects to this cause. So I can add an effect, choose the effect I want, and I can even specify what type of outage that effect applies to. So maybe a fire would only apply to failures, but maybe something like a loss of production would also apply to outages for planned maintenance. So I can create quite a detailed picture of the costs and effects of outages in my system. So we've built our hierarchy, we've populated it with failure data, with maintenance data, and we've specified the effects of failure as well. So now maybe we have enough information to maybe start looking at improving our maintenance strategy a little bit. So there are a couple of ways to approach this. One is you may choose to optimize each individual task in your project. So all your tasks may be treated independently, and you want to modify each one to get the optimum cost from that task. So there are a couple of ways you can view this from an interface perspective. I find the nicest way to demonstrate it is actually through the cause itself. So I can go to the Strategy tab, and I can see on the Strategy tab for my cause all the maintenance strategies I'm performing at the moment. So right now I'm only using a planned maintenance task. So I'm just going to modify the interval through here. So let's say I've built this system in the project to be as close to my real system as possible, and right now I'm doing this maintenance once every year, but I think maybe I can do better than that. So I might start by doing a simulation of this cause with the current maintenance strategy. Now, during a simulation, the program will run through a simulation of this cause, and it will do it, say, for a lifetime that I've specified. So in the project options, I might say the life of this system is 10 years, and it will repeat that 10-year lifetime 1,000 times or 10,000 times, as many times as I say it should. And the result that I see will be a mean over all those simulations. So that's given me the best possible statistics for my predictions. So for a 10-year lifetime, the program is predicting this cause will cost about $6,000, that I'll have on average about 44 hours of downtime due to failures. Perhaps the most important parameter if I want to improve my maintenance is this one, the cost-benefit ratio. This is the ratio between the cost of this cause if I do the maintenance as I have it now, which is basically this number, and the cost of this cause if I run to failure. And because this number is quite a lot less than 1, it suggests that my current maintenance is worthwhile. I am saving money by doing this maintenance. However, perhaps we can improve on this a little bit. So let's select that maintenance task and click Interval Optimization. Now, the way optimization works is that the program will test a range of possible maintenance intervals, and it will recommend the one that gives the lowest cost. So I can click here to specify the intervals I want the program to test. So I will try 50 possible maintenance intervals at increments of 1 month. So what this means is the program will run, say, 10,000 lifetime simulations with a maintenance interval of 1 month. Then it will go back to the start and do it again with an interval of 2 months, then 3, then 4. And what I should get at the end is a plot of cost versus maintenance interval. And what I want to see is a minimum at the maintenance interval that's expected to give the lowest cost. So we'll do that. And you can see here there is a blue trace that represents cost. And there's a nice minimum in that at about 6 months. So the program reckons that based on the information provided, the optimum maintenance interval is 6 months for this failure. Now you'll see also the program is plotting criticality. Criticality is coming from the effects. It's based on the severity numbers that we entered for safety, environment, and operation. And the program will plot those numbers against maintenance interval as well. And what that allows us to do is compare our criticality to limits that we've placed in our project options. So this helps us to ensure that for the interval we choose, we're still meeting with our requirements for safety and environment and things like that. So in this case, we're still okay. If one of these traces were to go above the relevant limit line, we will get a warning at the bottom saying that it can't recommend the optimum interval because we wouldn't be meeting with our criticality requirement. But we're okay in this case, so I can accept that recommendation. And you can see the interval is updated. So I run again, and now you can see the cost-benefit ratio has dropped by 9 or 10 percentage points. So we can see we get a significant improvement in cost by using this maintenance instead. So basically the program isn't just telling us how frequently to do the maintenance in order to reduce cost. It can also help us to determine how much more effective one maintenance strategy can be than another. Another thing we can do, as well as optimizing an individual interval, we could say, well, this is what happens if we do planned maintenance, but what if we did an inspection instead? So I might turn that off and turn on the inspection. I'll enter some basic data for the inspection. We'll say it takes maybe half an hour to do that. We need just an electrician to do it, perhaps. We'll give it a cost and some predictive data. So we might say we can predict the failure up to 2 months in advance, and we definitely find the failure if we inspect for it. So we can optimize that task in a similar way. And it's saying do the maintenance every 2 months, which we kind of expect from the PF interval we provided. If we accept that and run again, we see we get a cost-benefit ratio that's still pretty good, but it's still not as good as if we do planned maintenance. So we're not just optimizing the current maintenance, we can also try out alternatives and see if they're any better than what we were doing before. So we can do that for individual tasks. You'll see on the toolbar there's also a button that allows you to optimize all the tasks in your project at the same time. So the program will just run through the whole project and optimize all the maintenance in that project file. Now, the other option that you have is to optimize maintenance plans or task groups. So often in a system, rather than doing individual maintenance tasks, you will have a group of maintenance operations that take place as part of the same plan, and maybe they're all done at the same time as part of that plan. So let me show you a slightly simpler example to show you how that would work. So in this project, I've got these 2 maintenance plans. I've got one plan that represents the replacement of a motor and one plan that represents inspecting a motor instead. So in this plan, I've created 2 maintenance tasks, just like I did in the previous project, here and I think here. And for both of these tasks, I have added them to a task group. And the task groups are here. If I open up one of these, you can see I've specified a common maintenance interval for that task group. And I can also specify a cost for the group. And you can see there all the tasks that are listed in that group. So just like a regular maintenance task, I can optimize a task group. And you can see it's just working through that now. And it's recommending a maintenance interval of about 4 months for my maintenance plan. And if we look at the bottom in the grid, it's showing me the cost-benefit ratio, which is about 0.4, so it's pretty good. But then I might decide, well, what if I did a different maintenance plan? What if I changed my strategy to an inspection strategy instead? Well, in both of these causes, I've created an inspection. Currently, they're both disabled, but I can go in here, I can disable that task plan, that group, and enable the inspection group instead. I'll optimize that. I'll just work through that again. And this time we're getting a recommendation of about 2 months with a cost-benefit ratio of 0.25. So that's quite a lot better than the other plan was. So I can accept that. I can click here and see these side by side and decide, well, maybe this plan is better. So then you could send that to your CMMS or upload it to your asset management system, ready to be implemented in the real world. And just like with the individual maintenance tasks, there's also a button just here that allows you to optimize all your task groups as well. So you don't have to do them all one at a time. There is an option that lets you do them all at once. Now, let me go to a different project and show you some of the other interesting features. So this is actually a little sort of, that's the wrong one. Just let me find the project I want. that one will do. So this is just a simple little oil and gas example with a wellhead, a Christmas tree, and a choke valve as part of a simple hierarchy. Now what I want to show you here is the spare part optimization. Now you remember I showed you the spare parts earlier and how you can specify how many spares you store at level 1 and 2. The program can also help you to work out how many spares to store in order to minimize the cost of storage. So it's helping you to get a balance between the cost of storing the spares, but also the cost of extra downtime if you don't have enough spares. So I can switch the view here to the spare optimization plot. I can select the spare I'm interested in. Then if I click here, I can say how many spares I want to try. Now I can say, I want to try 0 to 5 at level 1 and 0 to 10 at level 2. And the program will try every possible combination of spare part storage and tell me which one gives the lowest cost. I'm only going to do level 1 for this example. So if I leave these both at 0, the program just ignores level 2. I can run that. And this is the plot I get back, and you can see at the bottom the program's trying having no spares in storage and just buying spares when we need them, or having 1, 2, 3, 4 or 5 spares in storage. The pink bar represents the cost of downtime because I haven't got enough spares, and the blue one the cost of storing the spares. And of course you can see the lowest here is given by storing 1 spare. If I store more than that, my storage costs are too high. If I don't store any spares, I have to, every time I have a failure, I have to wait for a month for a new spare to arrive, so my downtime costs are very high. So this is helping me to choose how many spares I should store. And this can be particularly important in maybe offshore applications where, it might be very difficult to get new spare parts from land. So you have to know what's the best number of spares you should keep on the rig itself. So I can accept that recommendation, and then the program will just update the spare with the relevant storage capacity. And as well as running individual maintenance maintenance optimizations and spare part optimizations, I can of course just run a complete simulation of the project where the program just does one lifetime simulation of the whole hierarchy and tells me, one set of lifetime simulations for the whole hierarchy, and gives me predictions about the lifetime cost broken down by the different cost drivers, availability data for each individual cause, occurrence data for the effects, and even usage data for the various resources, so I can see how many spares I expect to use, how often I expect to call out my engineers, and things like that. And that information can be presented as plots as well, so I can see maybe the cost profile over the lifetime and how that breaks down between the different contributing factors. Another useful one is the contribution plot, which shows me which failure modes are contributing the most to cost or to downtime, and again how that breaks down between the different causal factors. So that's an overview of RCMcost, and of course I'll talk to you next about AvSim. But before I do that, do you have any questions at all about RCMcost?
No, at the moment.
Okay.
This one. No.
Sorry, am I okay to continue, or do you have any? Did you want to discuss this for a moment?
David, just a question because we are in the operational stage of the plant. If you can give us an example, some of the projects that you deal on just using this. simulation. So how this operating plan can give, some ideas of the improvement that he can summarize from the simulations. Is it from the AvSim or from the RCM, if you have several examples?
Yeah, well, I think if you're moving on then to look at RAMs and the availability of the equipment within the system itself, the best tool for that is going to be AvSim. So the maintenance optimization RCMCost is kind of optimized for that, but AvSim is the best tool then for looking at the availability of the system. So I do have a simple example for that as well that gives you an idea of the sort of information you can get from an analysis. So this is a kind of simple oil and gas example that I use for some of the training that we do. Here I've used a reliability block diagram to represent the logic of that system. So here, for example, I've got 3 pumps as part of a 3-pump redundancy. I've created subsystem blocks representing a vessel and the associated flare system, as well as oil and gas outputs as well. Now the program allows you to build multiple systems in the same project if you wish, and you can see here the toolbar buttons for putting this together. You can add blocks, nodes, and connections to connect all this together, and you can select a block, click page down, and then start adding more structure inside that block and create what we call subsystems. So if I go back up to the top, you can see that's now a subsystem block with its own substructure, and like in RCMCost, there's no upper limit on the number of blocks or failure data you can create. You're only limited by the memory, and again, you have the 64-bit option there as well. So I've built this block diagram to represent my system, and on the left you can see I have a list of failure models. Now these failure models represent the failure and maintenance data associated with each type of equipment or equipment failure mode in my system. And if I open one, you'll find actually this information is pretty much exactly the same as what we've been looking at in RCMCost for causes. So you've got all the same failure data here, all the same maintenance information, and so on. I can add all the same details to the maintenance as well. So all of this is pretty much the same. And in fact, if you started off by building an RCMCost project to optimize your maintenance, and then you want to move to AvSim, if you go to the Tools menu, you can in fact convert directly from locations to block diagrams. So you can actually create a block diagram based on your hierarchy. Of course, that block diagram will be very simple, just with linear relationships. But once the data is in AvSim, you can then move the blocks around in any way you want. The other useful thing is that if you make that conversion, the program will automatically create links between the original cause data and the new failure model data. So if you modify one of them, you can come to this dialog and easily update the other side of the project with the new information, and so keep the two consistent with each other. But I can create these failure models and then just basically drag and drop them onto the relevant blocks. Each block can have its own failure model attached to it, or as you can see here, I've got 3 blocks with the same failure model. The program will still treat these blocks as being independent of each other. They will just share identical information. So it's like I've got 3 of exactly the same type of pump in my system. On the Rules tab, I can say things like what the maximum capacity of this particular equipment is in terms of throughput. This by default is a percentage, but as you can see here, I can modify the options and make the units up myself. And so I can say the maximum capacity of my system is 50,000 meters cubed per day, and this block on its own can handle 25,000. So the equivalent of 50%. So I can create blocks like this throughout my system to represent the failures and the maintenance, and then when I simulate, the program will be able to build a detailed picture of the availability and the criticality and the costs of my system. Now, depending on how much detail you have available to you about your system, you can actually model very complicated behavior in the program. So what you might have noticed on the block dialog is the presence of the rules box at the bottom. Now, rules appear in lots of places in this program, in AvSim. And for a block, for example, I can create rules that tell the block to do different things at different times. So, for example, there are lots of things I can change by phase. So I could say, I want to change the load factor by phase. This means that I am modifying the failure rate of this block depending on the phase of operation. So I can create phases. Here, for example, I've created 2 phases, summer and winter. And then I might say that during the winter, I'd set load by phase. During the winter, the load factor is 1.5. So that's basically increasing the failure rate of this block by 50% during the winter phase, maybe due to adverse weather conditions. I can create other types of rules as well. Another nice example in this project is in this output node, where I'm telling the program that I want to rotate this redundancy every time there is a failure. So there are lots of things you can do to model your system in very great detail if that information is available to you. Again, just like RCMCost, all of this detail is not mandatory. You can start very simple with just failure and repair information to get a ballpark estimate of availability, but then as more detail becomes available, you can then add that to the model and make it more detailed. You can also model things like a common cause failure. Here, for example, I'm using a separator in my gas output, but that same block, the separator, also appears in my oil output. So it's acting like a common cause failure. If the separator fails, both of these subsystems fail. And I can do that simply by copying and pasting that block elsewhere in the system. So we've shown how we can create blocks, create redundancies, tell the program what the maximum capacity of the system and the equipment is going to be. We can also say what the consequences of failure and partial losses will be. These are kind of like effects, only I can do this in a bit more detail in AvSim. So for example, I have this consequence I've created, which is a total outage consequence, and represents the cost of a complete failure of the system, as well as any severities I want to include. And this consequence is attached to my main system. So if I double click, you can see I've attached that stop consequence. But I also have things like maybe my gas loss consequence. This is a loss of capacity consequence. I can say how much it costs me per unit lost of capacity, and then I can say how much more it will cost if I fall below a certain target production level. So I can look at the cost of failure, but also the cost of a system which is still working, but maybe at reduced capacity as well. So if I click Start Simulation, you can see at the bottom there the program is simulating the system over its lifetime. Then I get the final results. Now one thing you'll notice is it says NPV costs. In the project options, I can include net present value information. Of course, a system like this is going to be quite long-lived, and over the course of 20 or 30 years, we might expect the value of money and the value of our product to change over time. So I can include the increasing cost of resources and the increasing value of our product in order to get a kind of weighted cost over the lifetime. And that's what you can see listed here, again broken down by all the different contributors to cost. So there's my system availability, where I can get estimates of downtime and mean capacity over the lifetime. And you'll notice that it's not just the main system I can do this for. The program is also giving me the same details for all the subsystems in my project as well. I can get availability data for the individual component blocks. So for example, the individual pumps I can see. I can see data for each consequence in my project. I can see a cost breakdown by phase. So I can see winter costs me a little bit more than summer. I can see again my spare part usage and labor. And if I was using equipment, I'd be able to see that too. So if you wish, you can also optimize maintenance in AvSim as well, and you can optimize spare parts. The process is quite similar. So, you would choose the task or the task group, specify the intervals, and then run the optimization. The thing to be aware of is that in AvSim, this process takes a lot longer. This is because the program cannot optimize each individual failure independently. If I optimize the maintenance for the pumps, I have to do that by simulating the entire system because everything is interconnected. I can't ignore what the rest of the system is doing. So for every simulation of the maintenance I do, I'm simulating the whole system, so it will take longer in AvSim than it does in RCMCost. Same is true for spare optimization. The process is the same. We test different numbers of spares in storage, and the program says how many spares we should store. So there, for example, we're saying the level 1 optimum is to store 1 valve locally. And again, if we run our analysis, we get plots which show us things like unavailability against time, or we can see cost against time. And I can also see things like capacity availability. Capacity availability is a useful tool. It lets us see the probability that the system will be operating at a certain level of capacity or higher. And I can do that for each, say, year of the lifetime. So you can see this option is quite similar, quite simple. If I had a more complex project, I might see something that kind of went more like this and dropped away to 100% at the top there. But then you can see roughly how much capacity you expect to lose, and you see it in quite a nice graphical way. So one of the things I was going to talk to you about was libraries, but the libraries actually work in quite a good way in AvSim. So I'll talk briefly about the libraries in their normal capacity before talking about how they work with AvSim. So a library basically allows you to grab another project, so say this one, for example, and attach it to your current project. And the advantage of that is you can now drag and drop information from one project to another. And this includes simple things like failure models and spares, but also you can drag whole bits of your block hierarchy or your system. So you might want to add that to your project. You can see now that subsystem is in my project as well. I'll get rid of that. So you can use the library facility to drag and drop data from one project to another. You could use parts of old projects for your new ones, or you can create dedicated library files that contain information you intend to reuse in other projects. So that's the main way in which libraries work. But perhaps one of the more useful ways it can work is in the capacity of comparing projects together. So I'm going to run this project, and I'm going to save it. And if I look at the plots and I look at contribution, I can see the separator is contributing a lot to cost. So I might decide, well, this is no good. I need to do something about that. Perhaps I'll introduce new redundancy to my system. So I will open a different version of this project. No, that's the wrong one. So maybe that one. So this is a different version of my project. Looks the same at the top level, but if I look at the gas and oil systems, you'll see that the separator now has a redundancy with it. So that's a temporary redundancy, a buffer, and I've specified in the redesign tab that it will cost me about $150,000 to install one of these buffers. So I can run that, and then I will save the results. Then I will attach a library, and what I'll do is I will attach the original version of this project, the one with the separator as a bottleneck, to my project as a library. So I'll just go and find that now, and that one. So that's now attached as a library, and let's give that a moment to find it. Yeah, and then I go to plots, and I choose the project comparison plot. And you can see here's the original version of this project, and here is the current redesigned version. Now the redesigned version has extra cost because it's got that redesign attached to it. But you can see that the operational cost due to consequences has dropped significantly. So that basically shows me that the cost of that of installing the redundancy would be worthwhile. And I could compare several different projects together. I might see what happened if I add redundancy, or if I buy better spare parts, or if I try a different maintenance strategy. I can see which of those options would be expected to be the most cost-effective for me using this project comparison facility. So that's really the power of AvSim. It allows you to simulate the availability and capacity of your system, identify bad actors, and then see what would be the best design change to make in order to reduce cost, reduce downtime. But of course, there are also tools there as well for optimizing maintenance and optimizing spare parts. And again, if you start off in RCMCost, you can use that data as the foundation for a new AvSim project as well. So that's an overview of AvSim. Again, it doesn't take as long because, of course, most of the information, the failure and maintenance data is basically the same for the two different modules, so I didn't need really to cover that again. But yeah, that's an overview of AvSim. Do you have any questions about it at all?
Yeah, I got a question. So you are saying it's better to simulate first bits of equipment use within RCMCost, then after that you simulate the block diagram with AvSim. Is that right?
I'm sorry, it's very quiet. Could you get closer to the microphone, or alternatively, you can also type the question into the text box as well. Because I can't quite hear what you're saying.
Okay. So can you hear me clearly?
A little bit. It's quite muffled.
Okay. Let me explain.
Okay, so I'll just have a look at this. So I don't want to say that it's better necessarily to start with RCMCost, because obviously I don't want to give you the impression you have to buy both of them. It's very important, obviously, that you purchase the thing that you need for your requirements. But the thing I'm trying to explain, I suppose, is that RCMCost is geared towards maintenance optimization primarily, whereas AvSim is geared primarily towards availability simulation. Now, the way RCMCost handles maintenance optimization is that it will simulate for each individual cause independently. So it treats the failures as if they are independent to each other. And that's why it allows you to optimize more efficiently. Now, if it's very important for your application that you take into account the interconnectivity between your assets, between your equipments, then maybe AvSim is better overall, because when you do the maintenance optimization here, it will take account of all the shared resources, all the shared spare parts, and things like that. It will be a slower process, but it will be more detailed. So if that aspect isn't so important, then RCMCost is a faster, more efficient way to do it. But if you do want to take account of that dependency, then AvSim will do that. It's slower. It doesn't necessarily mean it's worse. It's just it will take longer to do it, but it will take account of those details. So the Maximo portal. The Maximo portal works best and primarily with RCMCost. So if I show you a little bit of what that can do, let me see if I think I've got a good example here somewhere that will show us that. So I'll open this. So the Maximo portal will allow you to log into Maximo through Availability Workbench. So if I show you the options here, you can see where you give the program the location of your Maximo server and the username, and you can log in and then download information from Maximo. That information includes locations and assets. It includes failure classes, crafts and items, so your labor and spares, and also your job plans, so your maintenance. So you can basically use this information to build an RCMCost project. Okay, so I'll just answer this question then. Availability Workbench and Reliability Workbench approach different problems in the area of RAMs. So Availability Workbench is a tool for availability simulation and for maintenance optimization. If your priorities are availability, so uptime, downtime, if you're interested in life cycle cost and maintenance, and those are the things you want to model and to improve, then Availability Workbench is the tool you would use. Now, if you're more interested in reliability and safety, so you're more interested in avoiding certain critical failures, in improving the reliability of a system, and also maybe the human safety and environmental impacts, and also in the design of a system, then Reliability Workbench is the tool, because Reliability Workbench provides a suite of tools for well-established reliability techniques, things like Formica, fault tree analysis, event tree analysis, failure rate prediction. So if you're designing a system or you want to improve the reliability and safety of a system to avoid catastrophic failures and things like that, Reliability Workbench might be the way you go. if you're looking at the availability of a system and improving maintenance and improving lifetime costs, then Availability Workbench is the one you would use. The two are not completely exclusive of each other. It is possible to share information between them. So there you can see I can open up an RWB project, a Reliability Workbench project. So for example, if you were to use, say, the FAMICA module in Reliability Workbench during a design phase, and then you wanted to use that same hierarchy as the basis for RCM, you can import it into Availability Workbench quite easily. And the same can be done in the opposite direction as well. Yes, voting in Availability Workbench is very easy. So let me go back to my previous example, maybe that one. So the voting in AvSim is handled, let me go to my diagram, is handled in the output node of the redundancy. So there, for example, I've got 3 pumps. In the output node, I can just specify the vote number. Now, you can actually do something a little bit more subtle than that as well. So the vote number is really easy. I put 2 out of 3. And then if I have 2 pumps working, I'm okay. If 2 pumps fail and I'm left with only 1, then the system has failed. However, I might be in a scenario where I've got 3 pumps and each one can handle 50% throughput, and I want to have enough pumps running to meet with 100%. So then I want 2 pumps working wherever possible to meet that target. But if I fall below that target, it doesn't mean the system fails, but I will then be down at a lower level of production. So for that, what I can do is I specify the capacity of each block. So these are all 25,000 each. And then in the output node, I say the target is 50,000. So what the program will do is keep 2 pumps operating and 1 in standby. If 1 fails, then I will start up the extra block. If a second one fails, the system is still available, but it's then at a lower level of capacity. So those are the 2 options you have. You can just have a hard vote number, or you can have a target capacity instead and just kind of meet with the capacity wherever possible, but you can drop below it if enough failures occur to cause that. But yeah, you have both of those options available.
Okay. So actually, David, we are trying to see what is the tools which fit for us as an operating plant. So I believe that you have something like research all of the run tools. So what is actually the positive point from the AvSim and probably RCMCost compared to the other run tools?
So I didn't quite hear all of that. Are you asking what are the benefits of these tools compared to competing RAMS tools?
Yes, right.
Okay. So I don't know a huge amount about the competing tools. It's not always easy for us to get access to the latest ones. But I can tell you about certainly a lot of the virtues of these tools. Now, AvSim and RCMCost, as part of Availability Workbench and independently, have been around for a very long time. Now, I think the first version of AvSim was around 1990, and then for RCMCost, I think it was about 91 or 92. So these are both very mature tools. I know that we have an advantage, I think, in terms of user friendliness compared to some of the other tools, particularly RCMCost. I think some of the competing RCM tools can be quite complicated to use, whereas RCMCost even though it has many very powerful tools within it, it is still relatively easy to use. Another advantage, which I think we have over a lot of the competing tools, is the interconnectivity between the modules. So for one thing, of course, AvSim and RCMCost can talk to each other. And also you have an integrated Viable tool. I think one of our bigger competitors has a more sophisticated Viable tool. You may be familiar with Viable++, but our advantage is there's no intermediate stage between our Viable tool and AvSim and RCMCost. You can pass the result directly between them, whereas I think with Viable++ you may need to export the data and then import it to another tool. Yes, so as I mentioned right at the start, the software has very powerful import and export tools. So I can, let's say for example, go to export to Excel. I'll create a new Excel file with column names in the first row, and then I'll just very quickly give that a name. I will tell the program what data I want to export. So for this simple example, I'll just take the failure models, but I can export everything from the project. You can see it's all there. I'll just take that one data table. I'll take all the data from that table and then export. And then just to show you that quickly, there's the data exported from the software, and I can import this as well. In principle, you can completely construct a project from data in Excel. So yeah, that's all in place. No, it's not essential to purchase any of the portals. The portals are there if you think they'll be useful for you. So I know you asked about the Maximo portal a moment ago. If you have a lot of this asset data in Maximo, then I certainly think the Maximo portal is worth looking at, but it's not essential. As I mentioned at the beginning, you can build a project manually in the software, or as I've shown here, you can actually import the data from Excel or Access or somewhere else. Dynamic link library, that is a very specialized tool, and unless you have a specific requirement for it, I doubt you'll need it. Basically what the dynamic link library lets you do is, using say C# or Visual Basic, you can build your own utilities to load software into the project, run analyses, save data, export data. So the reason some people buy that part of the tool is if they've got their own very specialized asset management system, for example. So we obviously don't have an interface to their special asset management system, so they can use the DLL to build their own interface. So that's one way you might use it. Process reliability, if I go back to my example project, process reliability is similar to Viable. It's actually based on the Barringer process, and basically what it lets you do is perform a statistical analysis of your historical production data. So what you would do is, maybe over time, perhaps day to day, you would log how much oil, let's say, you produced from a rig, and you make a note of that. You can import that time ordered data, and the program will plot it on a cumulative probability plot like this one. You can then manually mark the cusps in the data, so every time there's a kind of sudden change, you put a marker there, and the program then breaks the data into those regions based on those markers, and the program can tell you then how much loss, how much capacity loss each region represents, and you can try and then associate each of those regions with a different failure mode maybe. And so you can say, well, okay, this failure mode is costing us this many barrels of oil per year. We may need to look at that. And you can try and use this data to get as close as possible to your nameplate or production level, basically your ideal level of production. So let me just quickly see what questions we've got now. So as enterprise. Okay, so I'll answer very quickly the enterprise question first. The enterprise system is for project management. It allows you to store your project files in an SQL Server database and thus control access to them. So you can control access by individual users, by groups of users. You can also have version control of your project, so you can create new versions of your project every time one is checked out and checked back into the system. You can compare those versions of a project and see what the differences are, who made the change, when they made the change. So the enterprise system is useful for when you have a large number of users and you need to keep control of who has access to what, and you want to be able to see a history of what changes have been made over the course of that project's lifetime. Let's see. I don't think you can do auto-synchronization with the Maximo portal. So we have certification from IBM for the Maximo portal. And one of the requirements of that, of course, is to maintain data integrity. If we can cause a problem for the Maximo data, then that, of course, would cause a serious problem. So basically, our upload and download has to be performed manually. You have to tell the program specifically you want to download data and you want to upload data, and there are buttons for that on the toolbars. So that just ensures that that the program won't automatically upload data without your say-so. So I think that's really part of our certification, so we probably wouldn't do that anyway. Oh, hang on, there's quite a lot of questions. Let me just see what this one is. Okay, so the LCC module is just an extra module you can get on top of AvSim and RCMCost. It basically allows you to create cost calculations. So if you, so in AvSim and in RCMCost, you can make predictions about the cost of maintenance, the cost of failure, and things like that. However, if you want to do a full lifetime cost analysis, you may need to include things like annual salaries and power consumption. These are things that are not handled in a conventional RAMS analysis or RCM analysis. So you can use the LCC module to add those costs to your project. So here, for example, I've created some global variables that represent additional costs that are not in RCMCost or AvSim. And I've created cost nodes that include cost calculations. So I can calculate customized cost profiles based on data that's in my LCC, but also data that I pulled in from RCMCost. So this value is the RCM cost, so that's what the R means, and that's the total labor costs. So this is the total labor cost calculated by RCMCost, and I can use that in my cost calculations as well. So LCC is letting you do a customized cost calculation and then plot those cost profiles on a cost plot. The plugin is a little bit like the DLL. It's a little bit smaller in nature, I guess. What it lets you do is create a small bit of code in the program which you can then trigger by selecting a menu option. I'm not sure I'm going to be able to see that here, but let's see. So if I go into application options, I go along, you can see their plugins. If I open that, I can create a new plugin, tell the program what type of code I'm using, and then I can reference all the assemblies I need for that code, and then I can just write the code directly into the software. And if I have a plugin in here, then I'll have a plugin menu on the toolbar. I'll be able to select it and then activate the plugin just by clicking on it. And what that will do is it will run the code, and then it will do whatever the plugin was meant to do. So some examples might be to import a specific data, specific bit of data from maybe an Excel file or an Access file, or maybe to run a custom calculation and then import the result of that into the program somewhere. So you can have lots of plugins to do lots of different things. Usually it's kind of import type tasks, but they can also do calculations and other things as well. And then I'll look at the AvSim question. Yeah, so basically, when I run the AvSim simulation, so I'll just run through that now. Obviously, I've shown you all the cost and availability data. If I look at the system data, I can see various parameters here, including downtime and unavailability, reliability or unreliability. F is shown here. So F is the unreliability, and that's just shown under the system data, along with all the other parameters for the various different systems. And it doesn't matter how many bits of data you have, it doesn't matter how big the project is, the program will estimate that data for your whole project. So when you run the analysis, it simulates the whole system, and if you look at that top level system, 1 in my project, it will show you unreliability along with all the other parameters. So that's just output as one of the standard results from the project.
Hello.
Hello?
Okay. Kalau misalkan review kita bikin dokumen atau di review setiap periode itu biar masuk review misalnya. David, we are just evaluating if, for example, we use the AvSim and the RCMCost. So normally the users, update the data is based on the project, or for example, in one plant of for example, you have the client of LNG plant. Did they, update the simulation on a yearly basis or a 6 monthly to update the reliability data and see what is the, the cost to produce the gas, the LNG or the oil?
Yes, so that's a fairly common thing for people to do. Is every few months or once a year, when more information has been collected in the asset management system, they might update their data. Maybe they've got more information about the labor or more historical data for the viable sets. You can update the model, run it again, and see if there's any appreciable change in the result. And again, this is an area where the enterprise system can be very useful, because of course in the enterprise system, the program can log every time you change the project. So you can see version 1 was maybe 2017, then version 2 might be from 2018, and so on. And you can compare the differences between the different projects as well and see what was modified. Did somebody update an MTTF? Did they add a new labor category? And you can see all of that in reports. So yes, certainly you would expect to update a model every time better data becomes available.
Yeah, we have, a challenge because we are on the operational state, and then I see that the AvSim is most likely suitable to the project phases, is it? And I see that probably RCMCost is more beneficiary for the operating plant like us. So if you have an example of what is, justification of selection of the software from your client or from the Isograph user in the operational phase like us.
So for yeah, I mean, what I can do is if I speak to Janet, we have a lot of partners, consultants who use our software, and they have case studies that might show the benefits of software for applications like yours, where people have used the software and seen benefits from doing so. I can ask her if we can get some information for you. That will be no problem.
Okay then. I think that's quite quite full. I mean, quite detailed for for us. I think that's what else? Yeah, I think that's everything that's already covered. What we want to see.
Okay.
Okay. Yeah, David, yes, it's very clear explanation from you that I'm surprised that this looks like one of the video that shows in the YouTube. You explained to us very clearly.
Okay. Yeah, no, it's no problem. Well, thank you very much for joining me today. What I'll do is I'll make the recording available as a download, so you can watch it again later if you need to see it again. And if you have any questions about the software, I think you have my email address, so you can ask me about that. If you want to know anything about, say, prices, or if you want to get a trial license, Janet will be able to help you with that.
Okay. Have you have information probably or any consultant use your software?
Yes, I'm pretty sure. Again, I can ask Janet to provide you with those details. That shouldn't be a problem.
Okay. Great. Okay. Thank you very much for your time.
Yep, that's no problem at all. And again, if you have any more questions, just let us know.
Sure, no problem.
Okay, have a good day.
You have a nice day then.
Thank you. You too. Bye-bye.
Bye.